Hey, good afternoon. Has everyone had a good lunch? Is everyone awake? This is going to be like a very soothing, calming kind of talk. If you feel like snoring, go ahead. Just don't disturb the person sitting next to you. All right. So my name is John Azariah. I work as a principal architect in the Microsoft Quantum Group. Our charter is to actually build a quantum computer. And as we'll find out during this talk, there's a whole slew of interesting issues that need to get solved before that. Can everyone hear me? Good? Okay. And so, in some sense, we're making strides doing what we need to do to achieve this objective of building a quantum computer. Some of it is what we're going to be talking about today. Feel free to come and get me if I don't cover an issue that is near and dear to your heart, which maybe I can't talk about publicly yet, right? So we can have a discussion about the theory behind it and all that. Fairly modest objectives. You should all understand quantum computing by the end of this talk. Well, understand why it is the way it is. We should be able to actually write our own quantum algorithms. Well, we'll create a little one and debug it, see how it works. And probably more importantly, understand the context in which any of this stuff makes any sense. Right? Why do we even need to have a quantum computer? What's so cool about it? What does it do? Why? Yeah, that kind of thing. So getting a sense of the big picture and seeing what fits into the, where this fits into the big picture is kind of important. So you should be able to walk away with that. Cool? I'll take questions at the end, unless there's something that completely mystifies you early, at which point, please raise your hand. Somebody will give you a mic, because this thing is being recorded, and then you can ask the question at that point. Cool? All right. So why quantum computing? So here's a little problem. Homework problem. If you factor that number into 2 primes, actually, if you could have done that a few months ago, you would have gotten $700,000. So you can go ahead and take your crack at it. It might take you a little time, though, because classically, that is actually like a little difficult problem. It's a difficult problem to solve. The purpose that we're trying to achieve is to use quantum mechanical phenomena to build a quantum machine that allows us to do that. And that's kind of the scale of the objective that we want to achieve. So let's go back to that problem for a minute. And there is a contest that takes place every year or so. This one is the RSA 2048-bit factorization contest. In 2003, it would have taken you 280, 300 billion years to actually solve the problem with the state-of-the-art hardware. In 2018, Azure has actually improved the situation 300-fold, which is still not quite good enough, right? And you can see the shape of that curve is basically Moore's law. It's that exponential thing. And as time goes on, all you're going to see is that curve sort of slowly moves to the right. And hopefully we'll get to the point where it's between 1 billion years, 1 million years, 1,000 years, and so on. Eventually, it should eventually catch up, maybe. I don't know. I don't know how long Moore's law will hold. But a quantum machine is going to change the trajectory of that curve. That's because this is not computing with a better Moore's law. This is not how to make Moore's law go twice as fast. This is about changing the way in which you do certain types of computations. And a 1 megahertz quantum machine should take about a day. A 1 gigahertz one should take about 2 minutes. And that's the idea behind that's the promise of a quantum computing approach. Now we'll talk about how it achieves that and so on and so forth. But before that, let's meet the top of the line here. This guy is not the fastest supercomputer in the world at the moment. It was until 2 months ago. This is the Sunway Tiahu light. It's a Chinese computer that occupies this size of a football field. And it is very, very fast. And it can even understand my favorite molecule. So if you think about what it means to understand a molecule, from a chemistry perspective, what we're really talking about is trying to figure out why this set of atoms, when you put them together, form a molecule that has these properties. And most of that comes from understanding how the electrons in the outermost shells of the various constituent atoms interact with each other. So what is an electron? Well, mathematically speaking, it's just a wave equation. So really what we're trying to do when we want to understand a molecule is to find the combined solution for a dozen, 2 dozen, 3 dozen, 170 electrons interacting with each other. And that's effectively solving a system of 170 electronic wave functions. Right? Now, we can do this for 1 or 2 electrons quite easily. I mean, this is a 3rd year, 4th year kind of exercise they give you when you study chemistry. Caffeine is a little bit more involved. So it does actually take a supercomputer. The Femoco molecule, which is the core of a very interesting substance, has what is known as a transition metal in there. And if you remember your chemistry and your periodic table, the transition metal is the set of metals that's between the 2 alkaline and alkaline earth metals and all the way up to the halogens. So somewhere in the middle of that, you have this block of metals that have really complicated electronic structures. And those really complicated electronic structures makes us what we are today. I mean, that's what gives us things like magnetism and all this other, high malleability and all of those things. Anytime you put a transition metal in there, the electronic wave function starts getting really difficult to solve. And actually, it is not tractable classically to understand that molecule. Now, I want to turn that thing around on its head, right? And I want you to think about what I just said, but think about it backwards, right? The Femoco molecule exists. That is to say, somebody has actually solved the equation of getting the lowest possible energy state to put all those atoms together. Nature's already done it. The math required for us to understand that is complex, so complex that we can't do it, but nature's actually done it already, right? So there is a natural phenomenon that's actually doing really difficult mathematics. So if you could take some problem that you have and beat it into a shape that nature can actually do the computation for you, then maybe you have some ability to solve a difficult problem that you can't classically solve using your computational skills, right? So I'll give you a slightly more weird analogy, but might actually help you. So think about the time of Archimedes. Go back a bit. They knew that if you flung a rock in the air, it would come down again. Okay, we're all, this is basic physics, right? I'm not saying anything that's too out of this world. But they didn't know where the rock was going to land, right? The computation of the parabola that was required in order for you to figure out, if I flung a rock from this catapult, will it sink that ship? That calculation was difficult to do. But if you think about it, nature's already solving that problem. All you have to do is fling the rock, and the solution will be found. So if you can somehow map your problem to the rock flinging piece, now you're in a position to actually take advantage of the advanced maths that the physics is already doing in order for you to be able to solve the problem. Now we understand parabolas quite well, so we don't go down that approach anymore. But I'm here to tell you that you can't understand this wave equation and you can't solve it classically. It's provably intractable to do so. And so this is us using nature to do the computation for us. Now that molecule I showed you is kind of important. Has anyone done any gardening here? It's the 21st century, very few people. Okay. So one of the cool things about, okay, how many people had lunch? How many people ate anything in the last 20-something years? All right. Every bit of food that you have eaten since 1911, from the rise of the industrialized farming age, started off being fertilized by ammonia that was made using a process that is extraordinarily expensive. The Bosch-Haber process was invented in 1911 by a couple of Germans, and it uses, at this point in time, 4% of the entire energy output of the world to just make ammonia. Think about that for a minute. Why do we need that? Because without ammonia, you don't get fertilizer. Without fertilizer, no industrialized farming. Without industrialized farming, no bread. Right? It's actually a very, very simple, straightforward line. It is the most important industrial chemical made in the world today. But before 1911, if you wanted to fertilize a field, and as a home gardener, you probably know this already, what did you do? You planted beans. Anyone know that trick? If you plant beans, it fixes nitrogen, atmospheric nitrogen. Doesn't do it at 5,000 degrees and 50 atmospheres pressure. Does it at room temperature and at atmospheric pressure. Right? How does that happen? Well, how it happens is in the root of the bean plant, you have these parasitic nodules that don't actually belong to the bean plant at all. They just happen to live on the root of it. And inside that nodule, in the cell membranes of some of the cells in there, there's a bacterium that knows how to take atmospheric nitrogen and water in an anaerobic environment and create ammonia and fix it into the ground. And it does it using the FeMoco molecule. So nitrogenase, which is the enzyme that is used as a catalyst for this, is built around FeMoco. And think for a moment now how profound it would be if we could actually industrialize that process to make ammonia. Great, right? The problem is you can't. Nobody knows how FeMoco works. In order for us to understand how FeMoco works, we'll need something like 2 to the 170 complex numbers to describe the problem. Right? So who's working this out in their head already? 2 to the 16 is what? Come on, Daniel. 2 to the 64 is the space that is allowed for you to access from RAM. Right? And that's actually more memory than has ever been created by the human race. Because 2 to the 50 is about a petabyte. 2 to the 60 is 1,000 petabytes. 2 to the 150 is roughly the number of atoms on the planet. So if you're going to store 2 to the 170 complex numbers to describe that molecule, you will need 1 million planets this size just to write the problem down. So now do you get a sense of why it's actually impossible to solve this problem classically? It's not about let's throw on a little bit more RAM. This will take every atom on this planet, if you could make it into a RAM cell, would only cover 1/1000th of the amount of information that you would need to just describe the problem. With the beauty of quantum computing, though, you only need about 170 qubits to solve this problem. And we'll find out why in a minute. And we will eventually, probably by the time I reach the end of my lifetime, probably be in a position to put 1,000 qubits on a 1 centimeter by 1 centimeter wafer. To give you a sense of how complicated that is, there's only 2 to the 250 atoms in the known universe. Right? So to describe 250 qubits worth of information, you couldn't access the whole universe and do it. But to be able to do that 1,000 qubits on a local device, that's kind of the approach that we're trying to take. So quantum mechanics is basically going to give us that kind of an advantage. As it turns out, it's not like a global sort of silver bullet. We'll come to that in a minute. So there are limitations on what kind of problems you can solve classically, what kind of problems you can solve quantumly as well. But these are some of the interesting ones. Each of these is effectively a $1 trillion problem. The RSA solution that I posted up there, the question that I asked you, that will require about 5,000 qubits to solve. You'll only need about 200 qubits to solve this one. So long before you go off and destabilize the world economy and start like breaking RSA left, right, and center, we might have actually solved a few really, really important $1 trillion problems first. And it turns out that you can actually protect encryption against quantum attack. So let's take a nice positive view of the whole thing, right? All right, how many people still awake? Everybody? Cool. Here's the fun part. How many people do anything with computers at all? Anyone? Binary? Comfortable with ones and zeros? I'm about to blow your mind. All right. So binary operations, who recognizes that? Anyone? How is that built? Does anyone know how the CMOS or MOSFET approach to build a NOT gate is? Anyone know how to do that? Cool. All right. One or two. Cool. So what is a computer? If you talk to a von Neumann specialist, which I think everybody here is, right? A computer is some abstraction that sits on top of metal, right? So if you talk to a C programmer, the guy says, yeah, I have an int here, but it's really a register somewhere in there. And when I flip a bit, it means something electrical. That's the abstraction that we are taught, right? That is a sugar-coated, fabricated lie. All right? So this is a gate that takes 0 to 1 and 1 to 0. But what it's really an abstraction about is it's an abstraction over mathematics. So here's a vector representation of a bit. So I'm going to take a bit and give you a single column vector with 2 items in it, where the 1 is in the 0th bit and 0 everywhere else, and the 1 is the other way around. With me so far? No problem. What does a NOT gate look like? It looks like a matrix that multiplies 0 to get 1 and 1 to get 0. This is basic matrix multiplication, right? I can walk you through how it works that way, but trust me that it does. Now I want to have 2 bits. How do I store the state of 2 bits? I have this idea of a tensor product, and what the tensor product does is it takes the second bit and multiplies it by each of the bits on the left of the first. So you have 0 tensor 0 is this vector, which is, let me see, it's that vector, which is 1 with that thing in there and a 0 and that thing in there. And then when you tensor the whole thing out, 1 times 1 is 0, 1 times 0 is 0, 0 times 1 is 0, 0 times 0 is 0. That's 0, because 1 is in the 0th bit, right? Brilliant. We multiplied 0 by 0 and gotten 0. It works, right? What about that? I'm tensoring 3 bits together. Strangely enough, you'll find that it actually works correctly. 0 times 0, 0 times 0 is still 0. No surprises there. What's interesting, though, is that the dimensionality of that vector changed. So having 0 on 3 bits made that vector space 2 to the 3 times as large. And now, if you think about it for a second here, we're using the transistors in our DRAM chip as a shortcut way of actually storing that thing. But if you go to the naked, unvarnished truth, what you're really talking about is a very large dimensional vector space that has just zeros and ones, right? And all the operations on them basically either shrink or expand the space. Now, I'm not going to do this, but you can if you feel like. If you want to represent 50 bits worth of information, you can take it from me that that size, the dimension of that vector will be 2 to the 50, right? And that should give you sort of a sense that, hey, something interesting is happening over here that people have just glossed over before. And they have, because the only numbers that you can put in there are zeros and ones, right? Now I'm tired of writing zeros and ones, so there's a little notation that you can do. That's called a Dirac notation, and we can actually basically use that notation as shorthand for that vector. So to look at the space of vectors with 2 to the 3, you can write this a 3-bit vector there. And that number should be familiar to you, because that number in the middle there is actually the binary representation of the thing that you want to compute. So Dirac notation is effectively what you've been taught without the ket vector on it. So if I tell you 0 times 0 times 0, you'll give me that string, and that string is actually just the binary representation, right? Now, I want to make life a little bit more complex. How many people know what complex numbers are? All right, beautiful. So again, everyone went through second grade, right? They talked about the number line. Again, sugar-coated lie. Because really what it is a plane, right? And you're looking at just the projection that is real. You've just forgotten the imaginary bits in the top and bottom thing. So I could take the vector and say that that vector is really just 1 and 0 with a 0 imaginary piece. And then that becomes effectively the ket 0, right? So now we're talking about the same thing. The complex representation is really what I've talked about, is just those 2 pieces in there, right? So now we have zeros, we have ones, we have a complex plane. Now, because it's a complex plane and you're talking about a point on the complex plane being 2 pieces of information, right? The vector is now 2 pieces of information. We have to draw this out in 4 dimensions. Well, I'm not that good at drawing, but I drew something in 4 dimensions, projected it onto 3 dimensions, and then squashed it down to 2 and drew it up there. So if you can follow what I've done right now, you have a kind of beach ball where each point on the surface of the beach ball is represented by 2 complex numbers. And all you have been doing so far with all of classical computing, everything that you've ever studied so far, has just dealt with the North Pole and the South Pole, and nothing else. So you have worked on the assumption and sort of the mirage, the illusion, that really the only thing that's there is that pole, the 0 and 1, and everything that you do is just flipping between those. And nothing could be further from the truth, because really, you could point at any point on the sphere of that beach ball and do pretty much the same thing. And as it turns out, when you do that, you have quantum computing. That's all there is to it. It's as simple as that. Because exactly the same representation that gave you classical computing from linear algebra gives you quantum computing for free, right? So imagine how easy it would have been if they taught us this in second grade instead of teaching us zeros and ones, but there you go. So now the only difference between the top and the bottom is the stipulation that the 2 points have to have a vector length of 1, because they are on the surface of this sphere. And if you have that, you can actually represent all of the quantum states that there are. And just to make sure, alpha and beta are both complex numbers. Now remember our friend, the NOT gate? What did the NOT gate do? Take the North Pole, stick it in the South Pole, take the South Pole, stick it on the North Pole. What does that look like? A reflection around the x-axis. That's actually what happens over here. It's the same friend we have there, same matrix. The x gate is actually the x matrix, the x transformation is exactly the same thing as the classical one. But because the classical one only deals with the North and South Pole, it doesn't have any of the other rotations. So if you want to rotate around the z-axis or the y-axis, or take something from the pole and put it on the equator, you have a few more operations that you can basically play with, because the surface of the sphere is effectively like a beach ball, and if you think about a dot on the beach ball, all you can do with it is rotate it. The dot moves as you rotate. So virtually every transformation on the beach ball is effectively a multiplication sequence of one of these matrix multiplications in there. That's really all there is to it, to be honest. Now, if you look at the matrix representation of a NOT gate, it takes alpha beta to beta alpha. Any alpha, any beta, not just the north pole to the south pole, right? So it's really a very generalization. It's a generalization of the classical world that we're familiar with, just an unfamiliar way of looking at it. Superposition, you probably heard of that. What does that mean? Well, it simply means this. Take the north pole and put it on the equator or anywhere else. And all that you're doing is you've got some linear combination of the 0 vector and some linear combination of the 1 vector to give you that point. That's really all there is to superposition. It means that any point on the sphere is a valid state. It's really all there is to it. And there is a special gate that does that takes it from the north pole and puts it on the equator. Now, the one thing that I haven't actually drawn out here, because it kind of makes things a little messy, is measurement. So if you think about the beach ball, and you do all this computation by rotating your state around and doing all this other stuff, ultimately you need to find out where the dot landed up after you did all the computation. And this is where nature doesn't let you look over the shoulder and say, what's on the copybook? Because this is a high dimensional space, but the only thing that nature will tell you is, hey, probabilistically it's on the north pole or the south pole, and that's it. So anytime you do something and you try to observe the qubit state, it collapses to either the 0 state or the 1 state. That's really why you get one classical bit of information out of a pair of complex numbers. And you can kind of work out what those alpha and beta are in that state because of the probability by which you get 0 or probability by which you get 1. The techniques that we're going to use for algorithms is to try and shift the bit state around in such a way that the result that we want becomes immediately apparent. Right? It's a very hand-wavy way of saying what it does, but let's just say this. This is the equivalent of flipping a coin, because now when you're in that state, you get a 50% chance of collapsing to 0 and a 50% chance of collapsing to 1 when you look at it. So you can take something in the north pole, which is provably 0, right? Put it on the equator and then measure it. And that will either give you a 0 or a 1. So it's a quantum coin flip, right? Okay, so I will now just put this on hold for the moment because, I think I've stunned quite a few people at this point, as I'm halfway there. How many people want a quantum computer? No one. No? Where are you going to put it? In your pocket? No. So here's what a quantum computer does not look like, right? That's not a quantum computer, that's a fridge. The quantum computer is a small little puck about that size that gets put at the bottom of the thing over there, and its temperature is maintained at 15 millikelvin. So you're not likely to get one to keep in your pocket anytime soon. You're certainly not going to keep one in your basement, right? This stuff is going to have to live in the cloud somewhere for you to be able to use it. So that kind of leads into the logical computation model in a minute, but I'll tell you what happens over there. Why is it that cold? Well, remember I was telling you about how measurement changes the state of the thing that you're looking at? Measurement isn't just you sticking a probe in there and asking, hey, what are you? It's not that it doesn't know that it's being measured until you actually look at it. No. Measurement is effectively what happens when it interacts with the environment. So if you want to keep your qubit state pristine and not actually lose out by interacting with the environment, you have to limit the environment. And one way to limit the environment is to come as close to absolute zero as possible. So there are lots of physical challenges involved in this. I mean, Microsoft's building the whole stack. There's control stuff happening at liquid helium temperature. There's stuff happening at 15 millikelvin temperature. Electronics don't work at 15 millikelvin. Like your traditional transistors will not work. So you have to have really interesting engineering challenges that you need to do to make this work. Think about just the wiring between keeping one end of the wire at 15 millikelvin and the other one at 4 Kelvin. And you'll have to keep the temperature constant. How are you going to do that? The engineering challenges involved here are phenomenal. And basically, Microsoft is solving every piece of that puzzle. Where I fit in is at 300 Kelvin, because I get chilly. I put on a sweater and sit down and write code, right? So I'm going to show you how the logical piece works in a minute, right? But this is really why the challenge of building a quantum computer is not just limited to getting a qubit. You have to build the whole thing, then put it in an industrial environment where you can actually access it through Azure. And that's kind of the model that that's in fact the only model that kind of makes sense, right? So from a logical computation model, has anyone done any programming of CUDA? Cool. So you have the idea that there is something called a coprocessor, which can do things that are hard for the standard processor to do. Guess what we've been talking about? We have hard problems that we have a coprocessor that does something. It's just that coprocessor doesn't sit in your box on a card speaking PCIe. It sits at 15 millikelvin and has to be connected over the internet. So any quantum programming environment more or less is going to look like this. You're going to have an adjunct coprocessor kind of environment where you write code in a host language, and then you come to the difficult bit that says, and this part is hard. Usually you comment it and say, this part is difficult. And then you say, I will write this piece so that it runs on the coprocessor. And then when it comes back, you take the results and then you use something else. And effectively, that is the programming model that we have at this point. So you have a host program that's written in pretty much any language you like, C#, F#, Python, any language you like at all. And then we have a domain-specific language that we've designed to express quantum computing sequences in. And that is in Q#. So a lot of the algorithms that already exist for quantum computing have been written in Q# already. They're completely platform agnostic, because they don't care which hardware they're going to run on. But the quantumness of it has already been captured in the Q# language. So today, the light green bit is actually freely available to anyone, including a simulator that will run on your local machine. So I'm about to show you some code in a bit that's going to show you how quantum computing actually works. All right? And so we have a simulator that either runs locally. You can run up to about 30 qubits or so if you have a good laptop or good desktop. You can go to about 40 qubits by going to the cloud. But remember that every 10 qubits that you go up effectively means you have to have 1,000 times the amount of memory. And so above 40 qubits, it starts getting a bit hard. To the point where if you can actually provably solve something that requires 65 qubits, it's almost certain that you have a successful implementation of a quantum computer, because you couldn't do it otherwise, right? Someday, we'll have the quantum hardware, and the quantum hardware will actually store the information, not as simulated mathematics, but actually in the quantum mechanical form, and have infinite precision and all of that other stuff. So how did we do this in the dark ages? By dark ages, I mean 2012, right? Or 13. There's a circuit on the left. It looks like a circuit that you would have drawn in electrical engineering, right? There's qubits going from the top to the bottom. A double line indicates a classical value. And then there's a whole bunch of transforms that apply on each qubit with time going from left to right. So the way to read this is by saying, OK, you take the message qubit, check to see if it's true or false. If it's true, apply the X gate to it, and then move down to process the message qubit in one way, and then move down for the here qubit, move down to the there qubit, and so on and so forth. This is actually how they did it before. It's actually impossible to implement things like loops in a circuit. You can't do it, right? So having a language that allows you to express the same thing, literally line for line on the other side, provides a strictly more expressive way of actually expressing the same program, but gives you a whole bunch of other interesting features, like the ability for you to compose functions, optimize, do whole program analysis, and then be able to shrink to the smallest circuit possible. So that is in fact the goal of the Q-sharp compiler, is to take general purpose Q-sharp code, fit it into the environment that actually will run the code, and then optimize for that. So this is kind of my day job. I mean, why do we build a language? So if you think about what the competitors are doing, they all, I mean, quite a few of them have different kinds of qubits. Not all qubits are created equal. But most of them have programming environments that basically allow you to interact with the qubit over the cloud, right? But they do it in Python with just a library. But if you think about what you need to do in order to be able to ship a general purpose function in a library of some kind, and then be able to use it in your code, you can't actually do it that way without knowing the underlying architecture. So you would effectively have to recreate the wheel every time, and you won't be able to compose nicely. Q-sharp is very, very functional. It's heavily influenced by F-sharp and a few other languages. Even though it looks like C-sharp and has a very familiar sort of look and feel to it, it is actually, make no mistake, completely functional, has partial application and a whole bunch of other really nifty things that allows you to basically have type systems that don't collide with the host language's type system. So now you can actually write reliable, sensible Q-sharp code that you can reason about. And that's kind of the background to it. So who wants to see some code? Right. So let's do the quantum weirdness demo. Let me give you, again, a little bit of background to this. So that H gate is the Hadamard gate. It's what we met earlier. It's the one that basically takes something that's in the 0 state and gives you something that's equally probable to be 0 or 1 when you measure it. But the quantum weirdness, think of it as a flip in the coin. Right? You take a coin, flip it, you get something. Where it starts going mad, how much time do we have? Where it starts going mad is if you put two of them together. So you flip a coin and flip the flipped coin. What do you normally expect? You expect something that's completely random, right? Two Hadamards in a row, unflip the coin. So these two gates, when you just put two of them next to each other, if you give it a 0 to begin with, it'll give you a 0 at the end. If you put a 1 in the beginning, you'll get a 1 at the end. So think of it as like interfering waves that just cancel each other out. But that's a very weird intuition to think of when you're looking at introducing randomness and all of this other stuff in the first picture. You're actually unintroducing the randomness at this point. What becomes really weird is if you measure in between. So if you look at the result, if you just look at the result of the first Hadamard, you go back to having random outputs, right? So from a quantum mechanical perspective, what you're really saying is, by measuring the result, I have now fixed and collapsed the waveform. So the second Hadamard basically works off of a collapsed value. So by just measuring in between, you can change the outcome of the thing, right? So that's a pretty weird piece of work. So let me go ahead and show you the code. So I have some C# code here. This is actually Q# running in a C# environment, which is exactly how you would do it. The host program is here. The main is basically run weirdness test on this thing called single Hadamard, followed by a double Hadamard, followed by something called observed Hadamard. Okay? So the three pictures I showed you, it's in that order. This is fairly straightforward C# code. Basically, we get the quantum simulator, and then we run the simulation that we want on it, right, which is actually passed in as a type argument here. And then we just bin the values that you get out so that when you get it, you can look at, say, how many did I get 0, how many did I get 1. So what did I do here? So the first thing I do is I run it with false as the input and then run it with true as the input. So I expect to get 6 lines of code, 6 lines of results. So single Hadamard passed in with false, single Hadamard with true, double Hadamard with false and true, and so on, right? The Q-sharp code looks like this. So we have something that takes an argument in here for testing the thing. But really what it is you allocate yourself a qubit and then flip the qubit if the input is true, call test on that flipped qubit, because qubits are always given to you in the 0 state. What you're doing is if somebody passes in true, you want a qubit to be in the 1 state. You're doing that here, and then you just run the test, whatever it is on there, and then set the result to be, if it's 1, return true, otherwise return false, right? So the single Hadamard is exactly what you expect. It takes a qubit, applies the Hadamard on it, and returns the measured value. The double Hadamard is Hadamard followed by Hadamard, and return the measured value. And the observed Hadamard is Hadamard, just measure it, throw away the result, don't even bother looking at the result, run Hadamard again, and return the measured result, right? That's kind of what we've done. So let me see. Start with that debugging. Let me see if my eyesight is that good. And Shift F5. So what actually is happening here is that the code that we're running, hang on, what happened here? What? Do I not have run on this? There you go. It's my eyesight more than anything else. What Q-sharp is actually a domain-specific language that is built on top of C#. So we'll actually generate Q-sharp code. Okay, so we have some results. And the first set of results that came back was, hey, I ran single Hadamard 1,000 times with false as the input. And when I came back, I got 483 false and 517 true. So that's roughly 50-50. Yeah? And if I passed in true, I still get false and true being roughly 50-50. So that's what we expect. When I run double Hadamard, 1,000 times I gave it false, 1,000 times I get back false. And similarly, 1,000 times true to 1,000 times true, right? And now I'm going to measure in between, and remember, all I'm doing is just measuring. I'm not doing anything else. And I get back the randomness in there. So 2 Hadamards can cancel each other out as long as you don't look at what they're doing in the middle. And that's part of the quantum weirdness. If you can fully explain that, you need to be standing here and talking, doing this talk. Because I still get weirded out every time I run the demo. I expect it to not work sometimes, and it never does. It always works properly. There you go. So Q-sharp basically is a domain-specific language. So we take these sequences, and we generate like C# calls for the simulator, or we generate like runtime calls for the hardware. So we don't actually have a qubit yet, but when we do those sequences will actually run on the hardware as a set of voltages and so on and so forth. Right. Let me see. What's the next thing here? How are we doing on time? We got another 15 minutes. So let me do a checkpoint here and see how many people sort of get a sense of the intuition for quantum logic now. Did it help that we started with classical and sort of generalized it to the quantum world to just show you that the thing's not entirely esoteric? There is actually some foundation to the madness, right? So you have a sense of that. And then we looked at some very simple code, and we kind of have an understanding of what the big picture is. We have 15 minutes. I'm going to be bold, and I'm going to try to give you a hand-wavy explanation of how to break RSA. Anyone interested? Cool. Breaking RSA. What's the problem? We have a large number that is purportedly the product of 2 primes, right? What we can do is, in parallel, try all numbers up to root n and try to see if they divide the number out, right? That's the brute force approach. And that's the thing that's really hard. Now, if you talk to the pop science version of what quantum computing does, they will say, quantum computers, they put multiple thousands of things in parallel, run all possible combinations, and one of them will be true, and you'll get that result. That's kind of how it works. It doesn't work like that at all. In order for us to figure out how to use quantum computing to do this, we actually have to find out something that is a problem of that is a structure of the problem itself, and then try to exploit that structure. So you're not trying to find the technique to find the factors of one number. You're going to try and see, hey, how does factorization actually work, and then try to get some understanding from that structure to see if we can use quantum computing for something. So, anyone recognize that sequence? Everyone recognizes the sequence, right? Now, how many people, this is 2018, so I find myself asking this question with some trepidation, but has anyone seen a clock before? Like an actual analog clock, right? It does modulo 12 arithmetic. Does everyone understand what that is? I'll give you a quick refresher. So modulo is what happens when you do the division and you look for the remainder. So it's the remainder of what happens when you finish dividing. So 4 modulo 2 is going to be 0 because 4 is evenly divided by 2, right? 16 is not evenly divided by 15. It has a remainder of 1, right? 2 mod 15. Well, it goes 0 times, but with a remainder of 2, right? So this modulo thing is kind of interesting. Turns out, let's do this. So let's take our sequence, which is 2 to the n, the bottom one, and then let's take the numbers on the top and look at 2n mod 15, 2 to the n mod 15, right? So what's the first value? 2. Next. Man, I'm typing really fast. Okay, any guesses on what the next one is? So, has anyone figured out the pattern here? Does anyone sense a pattern? It turns out that that is actually a periodic function, and it has a period of 4. And it turns out, and this is actually a result that is being used in the 1970s by a fellow called Peter Shor, who discovered that factorization is actually closely related to period finding. So finding the period of the sequence is actually kind of useful, except that it's not always going to be 2 to the n, it's something else. It's not always going to be mod 15 either, it's going to be something else. But if you look at this number, 2 to the n mod 15 is a periodic sequence with a period of 4. Everyone with me so far? All right. So if you take x mod n, and remember that n is the number that you want to factorize. If you take x mod n, x squared mod n, x cubed mod n, so on and so forth, that is going to be periodic if n is basically a product of p and q, and x is not a factor of p or q, then it will actually be in the period of p minus 1, q minus 1. P minus 1, q minus 1 is a multiple of the period. So by just looking at so what's the outcome here? If you take a set of numbers and do x cubed mod n, x to the 4 mod n, and so on and so forth, and try and find the period of that sequence, you will get a very good understanding of what the product of p minus 1, q minus 1 is. You might even find p minus 1 and q minus 1, right? So if you work out the math, it actually works out. In this particular case, the 2481 piece, you can actually look in there. So quantum period finding, though, where does this stuff fall apart? It falls apart because you can't find an efficient way to find this period, because you may have to go all the way up to n to see if it's periodic in the first place, right? So, okay, I thought that was you've got 2 minutes, the hook comes out. Right? There you go. But this period finding business works well, but it's still hard for a classical computer to do. So there's two things that you can do. One, in order to do this, there's one thing that is to prepare that sequence. That takes time, because x to the 15 mod n, you might need to go all the way up to 27 in order to find out if the period is 27, right? So now you have to exponentiate very, very large numbers. So you have to do something like there's techniques like mathematical, numerical, analytical techniques like the Chinese remainder theorem that allows you to basically compute the exponent of a very large, very large number, mod something very quickly without having to actually have overflow issues. But it's still computationally infeasible to do that. Now you need to find all possible values and then start looking. So that's the first problem. The second thing is, once you find this, how do you find the period? And that's another area. It turns out that in this particular problem, those two issues can be solved very elegantly on a quantum computer. There are basically polynomial time solutions for both of those problems. And that's what makes this algorithm work better on a quantum computer than it does on a classical machine, right? So one way is to actually create a large superposition of all the numbers in the sequence, right? And you can do that fast, and you can do that polynomially. And then I'm going to hand wave my way through quantum period finding. So we have this superposition and the period. Now, does anyone know what the Fourier transform of a function is? Okay. A quantum Fourier transform effectively means to try and find the peaks and valleys of the harmonics of a given function, of a given frequency, and see which one actually resonates. So I'll give you a sort of really hand-wavy analogy, right? So imagine a playground that has like n swings in it, and each swing is of a different height. Now, from physics, we know that each swing being a different height means that each of them has a different frequency. And if anyone has actually pushed a little child on a swing, you know that you can't just randomly push at any frequency. You have to push at the resonant frequency of the swing in order for the swing to actually have good motion, right? So if you think about some way of cloning myself, 256 times, and I have 256 swings of different lengths, and all of us push at the same frequency, then only one or its harmonic swing is going to constructively interfere with the push that I give, and all the others will destructively interfere. So if I look at the amplitude of the swing, statistically speaking, the largest amplitudes will end up being the ones that are resonating with the frequency of my pushing. So that's actually a very neat way of finding the Fourier transform of the function. It's just that this thing we're now doing in parallel rather than doing it frequency by frequency, which is what we would have to do in a classical sense. So it's a very hand-wavy, intuitionistic mechanism for trying to explain how we get period finding. Once you get the period, then you can actually go back and apply that sequence to figure out what the products are, and from there you can actually get the results that you want. And in fact, the whole thing is probabilistic, because even if you run Shor on a standard simulation of a computer, quantum computer, you will sometimes get the right result, and sometimes it will say, I can't find any solution, because probabilistically it couldn't find a peak in the period finding part of the algorithm, so you wouldn't be able to figure out what the period is, and then you basically have to run the thing again. So it's just all, the entire thing is all based entirely on probability, right? So this is not meant to be a sort of rigorous explanation of how Shor's algorithm works, but it should give you a sense of what kind of approaches people have to think about in order to be able to take a problem that has nothing to do with the physics of the thing and transform it into the quantum mechanical space to try and take advantage of what is available over there. So you remember that thing I told you about Archimedes and the stone flinging pit? This is kind of the mindset that you need to have to say, hey, take this problem, do this kind of thing, and that sort of closely aligns with what this thing can do, and now I get myself a benefit out of it. So it's entirely true that there's only a very small set of real algorithms that show any benefit or a quantum computer at all. The ones that do show profound improvement, but the other ones, we are still working, and the whole world is still working on trying to find better algorithms to do stuff. And that's it from me. So again, the objectives, go ahead and download the SDK, the QDK, and try it out. The language will be firming up into a V1 kind of version fairly soon. So if you want to have input on what features you don't like, what features you do like, get on it and tell us, because we're still listening to everybody before we bake the version in. It's important for us to know that. So that's it from me. Feel free to ask any questions. I think we have about 3 or 4 minutes. Yep.
The quantum computer, you said it sits inside a big fridge. So what does it actually look like? What's inside there, and how does it work?
That's a very, very good question, and it really, really depends. So the quantum computer that I told you about sits inside a fridge that looks like that. That's called a dilution fridge. Qubits are actually based on any quantum mechanical phenomenon that can hold 2 states. So there are quantum mechanical systems that work entirely by trapping photons, for example, or trapping ions, or just shooting photons around, or working with lasers. So different qubits have different physical characteristics and different sizes. So the thing that has to do with like shooting lasers, the qubit's basically about that big, or even maybe a little smaller. But the qubits that we're talking about are maybe in the nanometer range. So what's inside there depends on the kind of qubit there. There's spin qubits and dot qubits and topological qubits and all of that. The ones that are transmons basically have an interesting mechanism which uses electrons to it really depends on which qubit you want. So the ones we have are called topological qubits, and they use a mechanism to pair electrons, but pair electrons at a distance, so they become less susceptible to noise. And the physics of how that works, I can have a conversation with you about, but I think that's a bit much for the video, to be honest.
And is this available to the general public? Can we spin up an instance in Azure, or is this only for Microsoft Research?
So at the moment, Microsoft doesn't have a qubit at all. We are still working on getting the first qubit. The characteristics of that qubit, those are designed to basically be equivalent to about between 100 and 10,000 of other qubits that are available. Google has some qubits. IBM has some qubits. Another company called Rigetti has qubits. They're all transmon qubits. They decohere fairly fast. They have they've kind of spurred an entirely different kind of quantum computing branch called noisy intermediate scale quantum computing, where basically they expect that the qubit doesn't hang around much for a very long time, but still want to see if they can use it for something. Anyone that has a qubit only allows you to spin up and run an experiment with it over the cloud. So there's IBM and Rigetti and Google, I don't know, actually has not published a way of accessing the qubit, but IBM certainly has, and Rigetti certainly has. So you can actually play with a real qubit if you want. We have a simulator in the cloud for the moment, and we're still working on getting the first qubit. Anyone else? Cool. Well, thank you.